There's such high demand for this field. Like I would say 90% they got internships.
Really?
Yeah.
So hello everyone, today we have Amber here. He's going to explain the industry no one is talking about because he is part of the semiconductors industry, one of the most recession-proof industry in the US right now. And Georgia Tech से दोस्तों Amber के सारे batchmates are 90% in Apple, Nvidia और AMD, right? Because जब recession में software engineers were not getting calls, he was someone and his friends in electronics, communication, VLSI, semiconductors were getting the calls. So hi Amber, can you please introduce yourself?
Sure. Hi. So my name is Amber and I'm a final year student in at Georgia Tech, and I'm pursuing electrical and computer engineering. So my interest primarily lies in physical design or VLSI design, which is essentially converting logic into actual tape-out ready layouts. हाँ.
Tape-out is?
So tape-out मतलब होता है कि जैसे चिप है ना, तो TSMC आपको चिप देगा, ठीक है? तो वो चिप के लिए you have to send them a design. तो डिज़ाइन जब वो तो पुराने ज़माने में ऐसा होता था कि वो टेप पे बना देते हैं. तो हम लोग टेप भेजते थे. जैसे आजकल क्या होता है, हम तो हमारे पास सर्वर फार्म्स है, हम एक फाइल भेज देंगे, वो .gdsi फाइल होती है, वो भेज देते हैं एंड वो फैब्रिकेट हो जाते हैं. पहले क्या होता था, पहले टेप मतलब डिस्क टेप होती थी ना, जो भी टेप होता था उसमें स्टोर होता था डेटा, तो वो टेप भेजते थे एंड वो टेप से रीड करके उसको फैब्रिकेट कर देते हैं. टेप आउट मीन्स गेटिंग द चिप आउट. तो ये जैसे ना, ये CPU i7 CPU का लेआउट है
जी.
तो यहाँ पे जैसे कोर्स हैं, 4 कोर है, मेमोरी कंट्रोलर है, ये शेयर्ड L3 कैश है. इसको हम ये इमेज को भेजेंगे उनके पास, वो हमें ऐसा कुछ बना के देंगे.
ये TSMC को भेजेंगे?
हाँ. तो हम TSMC को ये भेजेंगे एंड इसको ऐसे में हमें फैब्रिकेट करके देंगे.
ओके, दैट इज फैब्रिकेशन.
हाँ, तो ये चिप हम डायरेक्टली लगा सकते हैं अपने आईफोन में और कहेंगे कि हमारा शुरू हो सकता है.
हाउ यू बिकेम अ VLSI एक्सपर्ट? अपनी बैकग्राउंड बताना. आपने अंडरग्रेड भी इलेक्ट्रॉनिक्स में की थी.
right.
सो व्हाई अंडरग्रेड इन इलेक्ट्रॉनिक्स एंड व्हाट एक्सपीरियंस यू हैड? हाउ यू गॉट इंटरेस्टेड इन इट?
I started my bachelor's with mechanical, and like in my first year I realized that I'm really good at electrical. Like naturally I was good at electrical engineering and electronics.
How did you figure out that?
Because all my friends, everyone around me was struggling with electrical, and I got like a straight A.
Oh.
Yeah, and it was like people were like actually failing. It was not even like it was getting B or C. People were failing, and a lot of people, even studious people, were like at C or B, and I was just naturally at A. I didn't find it challenging, and I really found it interesting that okay, you can solve circuits like this. So for me, that was just like one indicator that okay, I'm good at this. And in my second year, like I was doing this buggy project, right? We have that in undergrad. So like for me, it was like actually fun to design the logic, like IR, all the sensors, interfacing them with the microcontroller. It was actually fun. So I was like, you know, this is what I want to do. I don't want to do mechanical. So in my second year, I switched to electronics. And in my final year, I like during that placement time, right? I was interested in software because like all my friends were in software. So like everyone was talking about software, and there was a bubble in 2021 that software jobs were paying a lot.
Tier 2, Tier 3 college में 50 lakh package मिल रहा था सबको.
Yeah. Like it was highly bloated because just COVID खत्म हुआ था, तो everyone was just hiring, right? Because everyone was like, there's going to be a lot of demand. So like I also was like, okay, everyone's doing that, so let's do this. I didn't even know about VLSI. I didn't even know about semiconductor industry. And then like I think ARM came to our campus, and I got shortlisted for the interview. Like I didn't even prepare for the test, and I cleared the test. So for me, that was like an indicator, okay, like, and that's the first time I got to know that, okay, this is actually an industry. So then like I really tried for semiconductor, but I didn't get it. So I started as a software engineer at Samsung, right? And then soon after, like I left my software engineering job for an internship at Cadence.
Cadence is in chips?
Yeah, so Cadence is an EDA company. It designs the software, but I was in the IP design team of Cadence, so we would design our own IPs and sell it
property,
intellectual property, and sell it to other companies. So
basically chips sell karte.
Correct. So we make our own chips and sell it to other companies. So I did an internship there, then I got converted, and then I worked there for 1 year. Right, so that was like total 2 years approximately. And then like I realized that like I need to move into like I would say the core IP design part of this job. So like there were a lot of opportunities in US, and US is like the mecca for semiconductor design. So that's why like I wanted to learn from the best, and that's why I made the decision to do my masters.
Of course, like pure world ki, I think 90% of the chips are designed in US,
Absolutely,
right? Yeah. So like when you switched from Samsung to Cadence, was it because of your passion for chips?
Yeah, absolutely. I mean, I was decent at software engineering because I actually took electronics and computer engineering. So in my undergrad, I did I did some CS courses as well, and I was decent at programming. And I have been programming since I was like I think 15 or 16.
Oh.
Yeah, like since 11th, like I had been coding. So I was decent at programming. But then again, like my natural inclination was towards electronics.
So what was absent in Cadence? आप क्या miss out कर रहे थे Cadence में that you felt like going to US? Coming to US.
So I mean, I was in analog design, analog layout. So there it's like full custom, and it's pretty like it's more like it's a very laborious task, I would say. It's like just creating custom chips, and I wanted to automate some part of it. And since I knew programming, and so that's like the benefit of having this like extended skill set where you also have programming skills along with electrical skills. So then like I could use my programming skills to automate some tasks. And I learned some tasks, like I tried to automate some stuff, but I was like, I want to like go fully into this. And to upskill myself, I had to do my masters.
I see.
Yeah.
And by the way, dosto, in the US, I have been using the world's largest bank called the Chase Bank. And if you see the transaction history, I was charged $12 in the month when my balance was less than $1,500. And $15 when I received the incoming wire transfer from India.
Because of that, I decided to switch to a startup which is recommended by Rice University and University of Buffalo's website for all students, and even non-students can use it immediately because it charges you $0, nothing, when you receive money from India or anywhere from 195 countries worldwide. And you know, receiving money outside of United States, charging $15 on other banks can add up to hundreds of dollars over years, and you can save up immediately with just one step. And if you switch to it, first of all, it allows you to get credit history, 1% cashback every time you use it instantly, plus an ability to apply without social security number. When you're in India, you can use it, and many students have used it as proof of finance when they apply for visa by showing money in their Adro accounts. Go ahead and check out Adro because you will get $50 with my link in description below when you spend $50 after depositing $500 to your account. Go check out right now. Excellent. Yeah. So let's start with VLSI. What does it stand for, and a little bit about the industry you're working in?
Sure. So VLSI stands for Very Large Scale Integration, which essentially means that putting roughly about million to billion transistors on a chip, right? So the task of doing that is essentially called VLSI, and it starts from the architecture level. So you'll hear about like CPUs and GPUs, right? So those are architectures which are essentially an implementation of an ISA.
ISA?
So ISA is instruction set architecture.
Mm-hmm.
So for example, you know Windows 64, right?
Yes.
Or Mac OS, or you have like ARM now also. So you'll see like recent laptops, they have ARM 64 in them.
Ji.
So ARM 64 is an ISA. It's an instruction set architecture, which is essentially a language. Now someone needs to write something in that language, right? So people who write in those language are called implementation engineers. So or different companies have different implementations. For example, ARM has its own implementation, which it sells in terms of IPs. And you won't believe this, almost every company buys ARM licensed IPs for millions of dollars. So that's how they've made a business out of it. Like no chip right now is without ARM. Like if you want low power chips, you need ARM in it.
So IPs are kind of patents?
Not really. So in VLSI, IPs mean chips, like IP cores, like intellectual property. So it'll be like a block that a particular company will design and sell it for millions of dollars. So for example, let's say you're talking about Microsoft. They want to make a server chip, right? So they need one part which is like low power memory or low power or power management IC, right? So they'll essentially buy it from some other company, like maybe Infineon or even NXP or TI, and they'll pay like millions of dollars for that.
Oh.
Yeah. So this is how it works.
So designs are the most valuable asset. Right?
Absolutely. Yeah.
Yeah. I think I was watching, the interview of Arvind Srinivasan, who
Right.
is like the CEO
Yeah,
of Perplexity, he
Perplexity,
said that like, everything is at the end of the day a wrapper. For example, NVIDIA
Right,
is a wrapper
right.
of what TMC is
Yeah,
creating. And
yeah.
this design is a wrapper.
Right.
Is सबसे ज़्यादा intellectual asset hai.
right.
So I think NVIDIA like shining in this industry, that also
Absolutely,
shows.
yeah.
That's an IP,
Yeah,
right? That's
yeah.
$30,000 के लोग
Absolutely.
GPUs खरीद रहे हैं.
Absolutely, yeah.
So let's start with the basic little bit. Let's start with complete basics for students watching. So let's say we have a CPU
Absolutely.
and then we have a GPU.
Right.
So CPU mein, can you share what are the kind of skills you use? What is happening right now in your industry?
So CPU, essentially it's a very like I would say consumer focused market. So you have like consumer focused CPUs, for example, Intel has its own line and AMD, and like, whenever we go, like we want to buy the latest, like Apple has its own M2 and M4. So that's one segment. Then there's another segment which is server CPUs. So those are like for heavy load tasks, right? A CPU is essentially like processing information and data, right? So any task that you sort of want to perform on a server, it will get queued in the CPU. And for example, let's say I open ChatGPT and I want to send a request for an inference. So it will first queue that request using the CPU and then send it to the GPUs.
GPUs are three-dimensional, right?
Right. So you can say that like it's a brain versus brawn, right? Brawn is like the strength, and brain is like the one that's actually doing the control of or managing the tasks. So the CPU will manage all the tasks and schedule it for the brawn, which is the GPUs. So then GPUs will do it will process the information in parallel, right? But CPU cannot do that.
Correct.
So yeah.
So I think एक बहुत अच्छी example है.
Let me speed it up.
4, 3, 2, 1.
So let's say you are painting a big picture,
Right.
And if you do with a CPU, you will maybe just
right.
paint the nose and like एक बार nose
Right.
होगा, eyes होगी. But with GPU, the whole picture, whole face can be painted just at one time.
Right.
A big gun of a paint,
Absolutely, yeah.
and you paint the whole thing all at once.
Right.
Whenever we talk about CPUs and GPUs, we really need to talk about Moore's law. So Moore's law, in
Right.
which transistors double every 18 months.
Right.
Like लोग roughly 2 years भी कह
Right.
देते हैं, but
Yeah.
every 18 months transistors double, so the performance doubles as well.
Absolutely. Yeah.
So can you elaborate where does it come from, the
Right.
history of it, and where are we right now with this law?
Okay, so there's this engineer at Intel who co-founded Intel called Gordon Moore. So he released a paper in which he mentioned that, or he just observed that given the trend, every the number of transistors on a chip, they're doubling roughly 12 months, right? And he predicted that in the future this trend will continue, and he predicated that theory on the basis of that engineering effort will improve over the years. So engineers will keep on improving this technology, and we will see this rise in number of transistors on a chip. So it's also called transistor density or chip density. So
What is a transistor?
okay, so transistor is essentially like a switch, right? It's like a tap. So when you want to say that, okay, it's either on or off, right? So like a tap, like it's either on or off. When it's on, water flows through it, right? And water could be water is essentially just electrons, right? But what it does is that, for example, in memories, the way it is used is that since we have a binary function 0 or 1, right? It's on or off. So that's where the binary comes from.
And data can flow 0
Exactly.
or 1.
So now you can store data in terms of 0 and 1 in a transistor. And that's just memory. Now when you look at other parts of logic, so for example, when you're looking at let's say CMOS, which is a complementary MOS. So it's just like a logic gate. So logic gate, what you want is Boolean algebra, right? 1 and 1 should be 1 and stuff like that. So for that also, you can use transistors to drive that logic. And that is a very beautiful sort of method in which by which this thing happens, where you can actually create logic using these transistors. That's how Boolean algebra was like it came into the picture.
Now the question, you explained Moore's law pretty well, right? And transistors double.
Right.
But how do they double? Can you go in depth of it with Moore's law?
So there are a lot of methods. The most like basic method would be essentially to reduce the size of transistor, right? So that is the most difficult thing to do right now, especially because if you look at like the number of like the size of transistors over the years, even now like there are companies operating at 45 nanometers, right? But now we have reached like 1.8 nanometers and 2
nanometers. Yeah,
right,
it's so
3
small.
nanometers, right? So
the chips are becoming
absolutely.
smaller.
So, but the problem is the diameter of silicon atom is 0.2 angstrom.
0.2.
Or I would say like the diameter of silicon atom is 0.2 nanometer. And now we have reached a gate length of 1.8 nanometer, right? So that is the limit, right? And there are other limits as well because now you're at the edge of designing or at the edge of engineering, right? You've reached the limit. So now people are coming up with new transistors as well. Like instead of the traditional transistors, now they're coming up with new transistors. Like you have gate-all-around FET, and people are also looking at carbon nanotubes. People are looking at different material as well. So you have gallium nitride and all those things. So apart from that, like even if you look at like how we broke this limit, for example, we used to have planar FETs or something which is like two-dimensional, right? And then we broke that into FinFET, where we had added a third dimension to the transistor. So FinFET, the name came because like there's a fin in the transistor. So FinFET and technologies like these, they essentially cause Moore's law to keep growing, or they continue Moore's law. We
make it three-dimensional.
Right.
Just like GPUs are also three-dimensional.
Correct.
So that's how like Moore's law definitely applies to GPUs as well, CPUs as well.
Correct. This is what is driving the growth in performance in CPUs and GPUs. Like if we didn't create a new transistor with each generation, there won't be any performance benefits. So that's why we see these performance benefits. Like if you compare a chip of like let's say 2024 with a chip of 2017, let's say 7 years back, you'll see a dramatic change in performance. And that is partially due to the change in technology as well.
And why does it happen only in 18 months? We understood so far that a transistor ka smallest size possible is 1.8 nanometer. So how do we only be able to do it in 18 months?
I mean, that's just an observation. So it's just a number because that is what the trend was. And another, like, I would say, this is my opinion, this is my reason, like, my understanding, which is that if you look at, like, how much time it takes to make a new chip, the turnaround time is around 2 years or, like, 1.5 years.
Yeah.
It's not like software where you can, like, quickly make a new product and ship it, right? So the whole process, like, from, like, the architecture to implementation, it takes around 1.5 to 2 years.
So that's why.
Yes.
Now, you explained everything so well. Now, let's talk about the tech stacks. What do you do in terms of software, hardware, to make it possible, to possibly implement Moore's law, to possibly double down the transistors, to build hardware? So what do you do?
So I would say that there are like 4 major stacks or 4 major like areas. One is architecture, right? Architecture is like people who design these CPUs and GPUs who create the architecture for that. Then there's people who translate this architecture into logic. Logic means gates, right? So that is done through RTL design, which is register transfer level. So in that, like you use Verilog and System Verilog. These are programming languages. So these are hardware. So these are called HDLs, hardware description language. So using them, they're like C++ only. So now actually there are new things coming up like System C for verification. So System C is essentially similar to C. Like you have OOPS, you have all the concepts of basic programming. It's just that now you're designing for hardware, right? So that is one thing. Then you have like, if you go like below that logic, below that level, then you have verification, right? Verification uses like solid programming skills where you need like System Verilog, C++, C, depending on which thing you're verifying, right? Sometimes people need to also learn like OpenGL, Vulkan, in order to verify GPUs. Because what you're trying to do is you've designed the logic. Let's say the logic is for a shader, right, of a GPU. Now you want to verify that whether that shader works or not. right? So you want to render something.
What is shader, by the way?
Like, I don't think I have a lot of knowledge. It's just a part of like, for example, you know OpenGL?
OpenGL.
Okay. So it's like, how do I say, all the games, right? They run on these. So whenever a GPU renders a game, right, it needs a translation language, right? So these things, OpenGL, Vulkan, all these things, and shaders also, they help sort of translate this code into yeah, basically.
Okay, so these are the tools basically convert code into functionable hardware.
Right.
That's
correct.
what you're saying.
Yeah.
Okay, so these are the tools like
So
NVIDIA
okay,
भी use हैं.
I'll just actually back up about Vulkan. Vulkan is like a programming language only. Okay, so this is C++ है. तो उसका like they just use it to create like how do I say modules which can be used in testing. But essentially you are using like HDLs, which I mentioned, like System Verilog, VHDL or System C. That's one level. Then you have verification, which also uses the same languages, and C++. And then there's another like level, which is physical design. Now, physical design is essentially translating this logic, which you design in RTL, to actual layouts, which will be sent to fabrication units.
I see.
So they will be sent to TSMC. So now this area, like I would say, like you would need electrical skills. Like? For example, you need to know circuits. You need to be really good at circuits because there'll be a lot of RC ladders, like resistance and capacitance, right? All those, we had Thevenin and Norton's laws. So your electrical should be really good. And then like once you're good with the electrical basics like RCs and of course you need to know about transistors. So I would say MOSFETs, like reading up on MOSFETs. There's this really nice book by Kang, which is called CMOS, I think. CMOS by Kang.
MOSFETs क्या होते हैं?
So MOSFET is metal oxide semiconductor field effect transistor. It's like a transistor. Okay, so all these things, the abbreviation, like these things just explain like how the transistor works. Essentially, it's a switch. So using these switches, using 0, 1, we create the world of binary, which creates the world of architectures. So for example, you have 32-bit, 64-bit. What does it mean? It means that the instruction is in 32 bits. So you need 32 transistors, like 32 zeros and ones to decode the instruction, right? So more number of bits you have, more information you can encode. So that's why like you'll see that 64-bit will have more sort of granularity over the sort of OS. So talking about physical design, you need like electrical skills, you need MOSFET, transistors and all those things. Then another interesting aspect of this is that you need to know like I would say coding. So your programming should be good. Like this is a very sort of underscored area that people don't mention. People just say that like, you know, for VLSI you need to know electrical and electronics. And people just say that, oh, you're from electronics, electrical, right? But like in our field, in every stage that I mentioned, you need algorithms. Every field. And I'm not just talking about basic like greedy algorithms, I'm talking about graph programming as well.
Oh.
There is graph. So all these companies, there's these companies called EDA companies.
EDA
or
stands for?
Electronic Design Automation.
Okay.
So these companies create the software for our tools. So our tools, the tools that we use, right? There are some tools especially in our field like physical design, where you need to like draw the shapes or put these cells together, right, in order to make a proper layout. So there you need these tools like EDA software. So these EDA tools, they use all these things like graph partitioning and like divide and conquer along with graphs. Because now you're looking at, let's say it's a very simple problem. For example, if I say that there are two cells, right, and you want to route them. So it's like, you can say that it's like a similar problem to the ones that we had in DSA, like this start point is an end point. You go through all possibilities, right? You do a recursion and so it's like that. So we need to know those skills because our tools are built on like algorithms.
Okay.
So we need to know algorithms as well. And then there's one coding language called Tickle. And Tickle and Perl. So Tickle is TCL, and then there's Perl, PERL, or Python. Python is like the staple, like because
industry kiya tha.
Yeah, her industry exactly. So for example, like if you want to present any data, right, we need Python. We need, because in every field, like we if we can save, let's say 0.1%. I made I would say like, so in last semester, I made a presentation in a packaging course, which is essentially 3D IC packaging. So my presentation was that Meta was set to buy, I think, 30,000 H100 GPUs from NVIDIA. Okay.
They have bought the highest one, 200,000 NVIDIA GPUs.
So they have that future demand, and now also they have bought like 30,000 H100 GPUs. Each one costs like around, I think, 20,000. I'm not sure about the number.
25,000.
Right. So I made a case that I calculated the number for Atlanta's power, right? Like the power in kilowatt hours, right? How much amount does it, like in dollars, how much does it cost? And I said that if you can reduce the power consumption of each H100 GPU by 10%, you will essentially, I think it was $1.4 or $2 million that you can save annually.
Oh my God.
Right. That's
1.
Yeah.
Million?
2 million.
Okay, $1.2 million.
Yeah. You can save. And that is just from 30,000 GPUs. Now, imagine like server farms, right? Using so many GPUs. For each ChatGPT inference, you need like so many GPUs. And so that's why I feel like this field is pretty solid. And like there'll always be a demand to make power efficient chips, which actually save all these companies, all these software companies like Meta and Microsoft money.
मैंने भी पढ़ा था न्यूयॉर्क सिटी को रन करने के लिए the energy needed is 5 gigawatt hours.
Right.
Now that is the amount of energy all the AI GPU compute from all the companies in the US need in the next 5 years. That is the prediction made as per the source, the newsletter I follow called The Information. And that is insane. Yeah. So I think we really need to cut down the cost.
Absolutely. That's why this field, like there's such high demand for this field. Like it is. I agree that it needs a lot of skill to enter. And like even now, like when I play soccer, so like I meet some people. So they talking to me like about the career fairs and all. So they were asking me like, how come like this field is good, like your field is good. So I was explaining to them, and they're like, how can we enter this field? And he was like a CS major. So I was like, you actually can. Like there is a big skill required to enter the market, but you can.
Kaise? Like a CS student with not much about semiconductor industry knowledge or VLSI. Okay, not much VLSI knowledge.
Right.
How can they enter?
Right. So I feel that this is like a positive news for computer science students. They already have the basic skills, which is programming and data science. So data science is very big. Like you need to use data science to actually prove your theories, right? So if you're saying that I'm going to save this much power, you need to figure out, for example, let's say you have billion transistors on a chip, right? You can't verify each single transistor that whether this is going to save power or not. So you have to do like some approximations, and that's where data science comes into the picture. So you need data science, you need algorithms, as I mentioned, that algorithms are the staple of this industry, right? So they have those skills. Another interesting skill that they already possess is operating systems, right? So these are like staple computer science courses, and it's actually nice because if you know operating systems, you can make the jump to, I would say, architecture. Because it's like it's linked through this, so computer architecture is called like hardware, software, co-design. Right, because it's a co-design of software and hardware, where you're saying that okay, this is the language in which the software is going to interact with the hardware. So that's how they can enter computer architecture. And if, of course, like if they want to move into, let's say, logic design or physical design, they would require like basic electrical knowledge. So it doesn't take that much time, like maybe a few months, to just know the basics, like how does a transistor work. What's CMOS, how does logic, like how a logic gets formed using CMOS logic, right? And once you understand these things, like it's actually pretty fun to understand. So once you understand those, I think like you're all set to join this industry.
Problem ये कि resources इतने ज़्यादा नहीं है. For example, like you want to look at documentation. A programmer looks at documentation, all are available. Like, but if you want to find documentation for Verilogs, right? Verilogs, syslogs, it's a big challenge.
Absolutely,
And इसके कारण I just saw a vibe YC-backed startup
Yeah.
of an 18-year-old
Yeah.
who I'm possibly interviewing soon as well. So he's developing a way in which you just name a Verilog file or a syslog file,
Right.
आपको पूरी documentation readme बन जाएगी.
Okay.
Yeah, so which is really useful for like,
Yeah, that's nice,
hardware
yeah.
engineers, people at NVIDIA
Yeah.
and all these chips companies.
Right. So yeah, I mean, even I think most of the stuff I learned through books only. So like I would just like search for particular books, like let's say System Verilog tutorial or algorithms, and then I would just read the entire book to understand how you code this hardware. And then there's an interesting website called HDL Bits. I'm not sure who designed it, but you can use that. So it's like a lead code for hardware.
HDL bits.
HDL Bits.
HDL bits.
Yeah, hardware description language bits. So you can use that. It's similar to lead code, but for Verilog. So anyone who wants to enter like hardware design, they can use HDL Bits as lead code.
As your resources are, like, are you able to find Stack Overflow for these problems you face, or you just have to go through the route of books?
Yeah, so there are some Overflow like websites. I forgot the name, but there are like some sort of blogs where people discuss like all these problems. Because now the number is growing, right? So now there's a community which is growing out. So even I had this community of I think EDA Playground. So EDA, again, the same thing, right? So they have a website called EDA Playground where you could discuss, like, let's say I say that, okay, I wrote this code in Verilog, it's not working. So there are like 10 people who would like try to solve it. And yeah, I mean, because see, back in the day, this industry was not that well known, and it didn't pay much, right? So whoever was doing like this work, like they were actually passionate about VLSI. That's why they were doing it.
Absolutely.
Yeah.
Like, I think there's a huge demand. And can you share, like, is there like a limit to the innovation that can happen in VLSI and semiconductor industry? Like, what if, like, जो 3D implementation
Right,
आपने बताया,
yeah.
तो इस FinFET जो 3D chip है,
हाँ.
तो stacking chip और chip जिसमें हम छोटे transistors fit कर पा रहे हैं, is there a limit to this rule?
I mean, it's actually not yet. It's not proven. It's still undergoing. So, like it's still in the works. So
With 3D stacking of chips, there's no limit to the amount of power you can achieve through CPUs and GPUs. That's what you're saying.
correct. So I mean, now companies are like stacking chips over chips and creating chiplet technologies, and like this saves power, and of course it improves performance, because earlier what used to happen is like when you had a planar surface, so there would be chips interacting in islands. So you had interconnect, and this interconnect there was a lot of latency. So now when you stack chips over chips, they interact through this TSV or through silicon via.
I see.
And that is actually very low latency. So now you'll definitely see like performance improvement. So that is just one field. Like this is just a small field where people are innovating. Now there are hundreds of such fields. Like this is just transistor technology or chip technology. Then there's people working on devices, right? How to improve the transistor as well. Then there are people working on architecture. If you look at ISCA, right, ISCA, there's a conference where like people discuss computer architecture innovations.
SIGGRAPH bhi hai na?
Yeah.
SIGGRAPH mein, like,
Yeah.
NVIDIA CEO met Meta. That was
Yeah.
also one of the biggest.
Right.
So they discuss these things.
Yeah. So I mean, people are innovating in all aspects, and since यहाँ पे there are like 4 or 5 fields, right, that I mentioned, in every field people are innovating. So combine like the results you can see. Like if you look at even 2-3 years, right, two chips apart, which are 2-3 years apart, the performance change is incredible.
In this industry of chips, the delivery time is really high, और इसके लिए electrical engineering बहुत चाहिए होती है. For example, like battery का temperature बहुत बढ़ रहा है. You need to test all these tests. Is this like electronics work as well, or no?
So that is more like electrical.
But you did both, right? Electrical and electronics.
Yeah, but like so the difference between electrical and electronics is like whenever you're working at anything below 5 volts. Now it's even lower, but 5 volts, anything below 5 volts is electronics.
Okay.
Anything above that is electrical.
Okay.
So all these batteries, like especially for cars, they're like very high voltage. They have a lot of watts. Like they store a lot of power. So that is electrical. Like that delivery of power is electrical. When you're like talking about small chips like which go in the phones, those or like laptops or servers, they are like electronics. Yeah.
I see. What do you enjoy more? You're majoring in both.
So I mean, I would say electronics because it's almost similar to surgery. I would say like it's that precise because I think I'm not sure. I think the radius of like our human hair is like in microns, and we're working in nanometers. Like it's like very very minute, and it's like the best part is it's like designing a city because you don't just have like X and Y. So it's not just 2 dimensions; it's 3 dimensions because now you're also going up in terms of metal stack. So it's like a routing problem for like a city, for example, right? And you have to, there are like signals and powers, like for example, highways and interstates and all those things. So routing those things, and I think there's a lot of constraint in that. And it's really fun, like dealing with those constraints, coming up with like really innovative ways to solve these problems. So
it's like you're creating your own world, right?
Absolutely, yeah.
So in this design, like what is the difference between hardware engineering and electronics and electrical engineering? आपने electronics और electrical तो explain कर दिया, but where does hardware engineering come into this?
So like in electronics there are other fields as well. For example, you have embedded systems, Internet of Things, you have communication. So that is electronics in a whole, and I would say hardware comes within the sphere of electronics, but hardware is just anything related to, I would say, silicon right now. So anything that you're making, like for example, if you're making chips, that would be considered hardware tech, I would say. Yeah. So for example, if you're making chips for an iPhone or a smartphone or some laptop or maybe some server, that's called hardware engineering now.
Okay.
So yeah, I mean basically anytime you're making chips like in silicon, it's called hardware engineering.
So what is your role?
Right. Okay. So my role is, as I mentioned, it's essentially converting logic, which is in terms of gates. So there'll be a lot of logic gates. You have to convert that into a layout, which is sort of an image, and then you give this image to the fabrication unit, for example, TSMC or Samsung or some fabrication, and they will take that image and essentially using lithography and etching and all those technologies, they'll just etch that image on a semiconductor, so on a silicon.
I see. And ऐसा क्यों है कि इस process में time क्यों लगता है? Why TSMC takes 2 years?
So it's not just TSMC. It's like maybe tape out would take like 3 months or 4 months, right? But
Tape out?
Tape out means essentially fabrication of this chip. So when, like for example, if I give my like layout to TSMC today, it'll take 4 months or 3 months for them to like etch the entire chip or create the entire chip. And that is because like it's a very complicated process. You have like lots of processes, right? So that's just 3 or 4 months. But majority time is taken to design what I am talking about, like layouts. So layouts take like 1 year.
Oh,
yeah, because
so your work is taking the most.
Yeah, 1 year, like I would say. Yeah.
So, is puri industry mein there are like parts to it. Can you break it down like stage 1, stage 2, stage 3?
Correct. Okay.
So let's understand the step by step.
Absolutely.
And
so,
which stage you are in?
Okay. So it's a top-down approach, right? So you have the architecture, which is essentially CPU or GPU. For example, CPU mein there's this thing that do you want to go with RISC or CISC? Right, or you want to, for example, you want to have a 5-stage pipeline or 10-stage pipeline, right? So architecture people will decide those, right? And then they will give this architecture to the logic design team or the RTL team. The RTL team will convert that architecture specification into Verilog code, right? Or a system Verilog code, which is essentially an HDL. Now that is called logic, right?
Okay.
Because that can be synthesized into a sort of chain of logic gates, and once you synthesize that, that's when I come in and you say that we want to convert this chain of logic gates into a layout. And layout there are a lot of constraints, like you need to meet the LVS, which is basically checks. So you'll have LVS, EMIR, all those checks. So you need to meet those checks, meet those constraints, and once you meet those constraints, so meeting those constraints only takes like 1 year. So yeah, so because it's like, and it uses like your electrical engineering knowledge, it uses CS knowledge as well. So using these things, you essentially finally cover with a layout which you can give to fabrication units.
Interesting. In तीनों में, like the job before you is hardware engineering, you say?
So this entire process is called hardware engineering.
Okay, this
Yeah.
is the, okay,
Yeah,
now
yeah.
I समझ
Yeah,
गया पूरा.
yeah, yeah.
So this entire process, stage 1, 2,
Absolutely.
3 is hardware
Yeah.
engineering. You are in a small part of it,
Correct.
which is like the electrical and electronics
Absolutely,
design,
yeah.
converting logic gates into the next stage.
Correct. Yeah.
Okay, this is
Yeah.
awesome. Okay, let's talk about the industry.
Okay.
Georgia Tech में कितने students को VLSI की industry में jobs मिली है?
Yeah, I think a lot of people, like everyone that I know in my batch, like most of them, like I would say 90%, they got internships.
Really?
Yeah.
So इतनी demand है, like
Yeah.
like ज़्यादा students choose नहीं करे, आप कह रहे हो कि class size full है कि नहीं है?
Class is full. So class size is like, I mean, people are like, there's a lot of competition to get in this. And once you get in, like even the other universities, like you have UT Austin as well. So वहाँ पे there are like, I think 30 students in the batch of ECE. So 30 or 40.
Wow.
So like in VLSI. So all of those, like they get like, there's a 100% conversion in terms of jobs. Because it's so selective and there are very few people
And why would you say it's a recession-proof job?
Okay, so like I would just say that this thing like requires a lot of knowledge, one, and the problem has not been solved yet. It's taken like I think 50 years, and it's going to take more time to solve this problem. So this is not a problem that you can solve. For example, it's not a product that like software you can just like create it in 1 month or 2 months, or like I'm just saying like basic product, right? So it takes a lot of time, and there's still a lot of aspects, as I mentioned, right? Lot of aspects which haven't been solved yet. There are problems which are like, which still exist and nobody has a solution for them. So that's why I would say like,
Example बताना.
for example, like you have transistors. So transistors now, we started with like some microns and then we came to nanometers. Abhi like I think 2014 or 2017 we were stuck at like 14 nanometer. Then we came to 5, 7, 5, 3, 2, 1.8, and now people are like, okay, we've reached this thing. People take this for granted. People take, okay, we will every year new smartphone comes, we will get a performance improvement, right? But this comes at a cost. Like this is because people in hardware tech are doing are creating and are innovating. So like this will continue, and people demand the same thing. They demand that each year our smartphone should improve. So that's why this is like, this demand will always exist.
I see.
Yeah.
क्योंकि नहीं तो लोग iPhone लेना हर साल छोड़ देंगे.
Yeah,
like,
exactly.
You know, it's a culture.
Yeah.
People
Then
know that
there's
it's
no
better.
difference. Yeah, exactly. And there's another aspect, actually, very interesting aspect regarding the AI boom, I would say. So as we know, like we are in an AI boom, right? So like people talk about like, okay, we're gonna come up with new LLMs, new software, which is good. Like there's a need for that as well. But all those things, they need compute, right? Nvidia is winning because of this. Like they have the solution, right? So even Nvidia needs people who can actually deliver a chip. So they also, if you read, like they had an issue recently, their chip didn't ship.
Blackwell is delayed by 3 months.
Absolutely.
Yeah.
So why? Because they had some issue with the tape out. So it's in hardware where they have a bottleneck, right?
TSMC में.
Right.
Yeah.
Not TSMC, but it's within their own organization in hardware.
Okay.
So they have their own hardware team, right?
Yeah, hardware design में problem,
Yeah.
right?
Yeah. So there was a problem in the hardware design, and once they got a test chip, I think it didn't work out well. So they're like, okay, we need to fix this, and that's why now they're gonna like do it again, like go for tape out again. So yeah, I mean, even there, like the bottleneck is not software. The bottleneck is not architecture. It's actual chip implementation or getting the right layout out.
Ooh.
So
And you're the one who figures out
getting a successful tape out.
bottleneck कहाँ पे है? इस फैब्रिकेशन में ज़्यादा bottleneck है या फिर लेआउट बनाने में ज़्यादा लेआउट में ना, राइट?
हाँ, मतलब अब एक्चुअली ये ना मतलब बहुत ट्रिकी क्वेश्चन है, बिकॉज ये हर जगह बॉटलनेक है, बट कौन सा बड़ा है मेरे को ये नहीं पता. आई वुड से कि TSMC का बड़ा है, क्योंकि उसका इम्पैक्ट देख लो ना आप. लाइक उसमें क्या है कि TSMC है, देयर आर ओनली कितने 3 या 4 प्लेयर्स हैं
जी.
यू हैव TSMC, Samsung एंड आई वुड से Intel, राइट? ये 3 हैं. सो clearly वहाँ पे there's a bigger bottleneck and as compared to like design team, because design में देखो कि there's so many companies doing design, तो bottleneck वहाँ पे असली आ रहा है वहाँ पे, because it takes like, I think it costs billions of dollars to fabricate a chip or create a fabrication unit.
और या इससे भी बड़ी bottleneck है कि TSMC जिस कंपनी से lithium ion लेती है, that is just one. That's the 90% provider for lithium ion.
Right.
And like, you know, it's insane.
Yeah.
क्योंकि TSMC के पास एक ही आगे player है.
Yeah.
उसका competitor ही नहीं है.
Yeah.
So
yeah.
that's also so true.
Yeah. So yeah, I mean, like, this thing also, like, design companies are very few. Like, there are a lot of design companies. There are very few fabrication companies. Let's say TSMC. So, for example, let's say if TSMC doesn't exist, right, tomorrow, then all these companies like Nvidia, AMD, Apple, sabko they'll face a shortage of chips because everyone uses TSMC. Even Qualcomm switched from Samsung to TSMC.
Oh.
Yeah. Because of the quality.
Insane.
Yeah.
Okay, now अब बेसिक से बात कर लेते हैं. अभी एक CS स्टूडेंट को इस इंडस्ट्री में, आपने बताया इस इंडस्ट्री में डिमांड बहुत है, क्लास साइज भी फुल है, बट हर एक को जॉब मिल रही है. सो हाउ कैन पीपल टेक एडवांटेज ऑफ इट? एक रोड मैप बना सकते हो कि स्टेप बाय स्टेप कैसे इस फील्ड में एंटर कर सकते हैं, स्टेप बाय स्टेप,
फॉर अ CS student?
हाँ.
Okay, so CS student, I mean, I would say that first thing that to do is, like, if you think that you want to do RTL design or physical design, you would need to learn like digital electronics. So, like, let's say if you want to do RTL or because architecture mein to easy hai. It's like you just like, you know, operating systems, you know, algorithms. So you just like learn more about some hardware software co-design, and that'll be good enough. But for this thing, and even compilers, for example, compilers is also a nice field for hardware software co-design. So let's say if you want to go for RTL or physical design, which is one of the more demanding areas, there you need like you need to know like basics of electronics. You need to know like CMOS, MOSFETs, transistors, all the logic, like electronics. Like you need digital electronics, analog electronics. Analog not that much, but digital electronics at least, from CMOS till logic gates till Boolean algebra. So that, and like you already have, CS students already have that algorithms, they have I would say data science as well, and like, yeah, those are the two basic like things that you need.
And after these skills,
Yeah.
what kind of interviews are like asked? Like DSA पूछते हैं इसमें भी?
No, so इसमें like they start with like basics. So if let's say you're a fresher, right, you have absolutely no knowledge of VLSI or you have no experience with VLSI, then like they would expect basics of electronics. For example, CMOS. They will start with CMOS. They want you to know how like digital logic works. Once you know that, look, so that's why I was saying that if you can understand that, and it's pretty interesting. It's like you'll connect the dots and you'll be like, okay, this is actually making sense. Once you can do that, then I think they'll actually move to algorithms. They'll ask you puzzles. So
Example बताना.
For example, I remember when after my undergrad, I gave the VLSI interview. So I was asked this question that there's a fly in a 3D cube, right?
Oh.
And you want to what distance? What is the shortest distance for the fly from the? I think it was one corner, let's say top right corner, to another face, the center of the face of the thing. So it's like, okay, so it was like from one corner to the center of the edge. Another center of the edge. So it's like then you have to know like what's the body diagonal and stuff like that. So, and because you need these skills to do routing and all, right? So yeah.
If you had to restart your journey, जितनी आपके पास अभी knowledge है, how would you do things differently? क्या आप US सीधा आ जाते हैं?
I would say like if I knew what I know now, I would start like I would try for like some high level roles. For example, so this is like considered back end of the hardware tech. Front end is architecture and RTL. So if you start with RTL and architecture, it's very easy to move into the back end because now you know more about the logic. For example, when you're just in back end, right? I've always been in back end. So I was just given designs and I was told ki just make a layout for this. I didn't ask, like I wasn't supposed to ask that, why is this happening? So there was no like opportunity for cross question, at least in Cadence. So that's why like I wanted, like, if I could, I would have gone into like a higher level, like front end, so that I can also learn about designing and then eventually move into back end. Yeah. So that is one thing that I would change.
I see. Is there any exit strategy you would say in this industry?
Exit strategy as in?
Exit strategy मतलब अगर आपको company छोड़नी हो, what is the strategy you use? मैं बताता हूँ, जैसे कि for example, I was reading Andre, who is the AI lead of Tesla, right?
Right.
He said he left his job at Tesla because it became very managerial. Technical नहीं थी.
Right.
आपके लिए क्या point होगा? You think you would quit this industry?
Like a make or break sort of situation. It would be a very big thing for me if I'm leaving it. Like, I would say probably if I'm not feeling that I'm able to create the impact. Like, if my work is not impactful enough, I would leave the industry. Like abhi, it's like if I'm gonna work for a company, right? I would want that I'm actually saving, like in terms of power, performance, or area, something I'm reducing, right? I'm helping them save money, because if you save area, it's like, so in semiconductor industry, area is in terms of US dollars. Because the more area you save in terms of your chip, the more like you will save in dollars. So like I want to contribute to that.
Excellent. Yeah. And last would be, what will be the salary expectation? अगर कोई student देख रहा है जो enter करने वाला है इस industry में, what can they expect out of the semiconductor industry? India में packages and US में?
I would say India is pretty good. Like
50 LP easy.
Okay, so like fresher ka, I would say like you can expect 20 to 25, and like right now I would say it's even more bloated, especially like because of a company like Nvidia. Nvidia is like changing the entire industry, because they are paying their employees so much that other companies also have to catch up, right? So I would say 20-25, and eventually like the thing is that as you like go higher in that thing, like you have more experience, right? Your salary like exponentially increases, because there are very few people in the middle, like with 10 years experience or 7 years experience. So that like sort of is a very big thing, I would say.
So Georgia Tech से जो जिनको job मिल रही है, like electrical engineering से, electronics से, in semiconductor industry, like is it like close to software or more than software, you'll say? Like 150K, 200K, like
I don't know what the salaries in software are. Like could you give me an example?
Like 120K to 150K, I'll say, software.
It's similar to that then.
Similar to.
I would say in some cases it's more than that. And especially now, like now to very few companies are hiring in software, right? Like I know some people in CS at Georgia Tech, and they're also like struggling with full-time jobs, and they have to like settle for like something which is non-ideal, I would say.
Yeah. So इस industry में भी ऐसा नहीं है कि supply कम है, but you can enter and break in because इसमें scope हमेशा रहेगा.
Absolutely, yeah.
Excellent.
Yeah.
Awesome, yaar. Thank you so much. It was wonderful talking to you. I learned a lot. I hope this video adds value and students gain some wisdom and can enter this industry and break in. Thank you so much.